like in one sample case, we can also make a test. In this case, it's called two-sample t-test. But in case of two samples, actually, a lot of things will be simplified. Let me show you that. Well, first of all, let me remind you that this is what we got by assessing individual outcomes. And then we also find out that this is the observed effect. And in the previous video, we learned how to estimate the confidence interval for the theoretical expected effect. However, in many cases, your task is not just to estimate how big the effect is. Your task is also to find out how likely you got this effect just by chance. What it means? It means that if you repeat this experiment not 4 times each, but 4 billion times each, and then in this case you will see no effect. So the real effect, the theoretical effect, is 0. There is no effect. For example, you compare medicine and control group, the treated patients and control group, and in fact your medicine doesn't work. So that's exactly what we call no effect, right? In this case, we talking about time, the effect of time on the popped corns, the percent of popped corns. So this is our expectations in this case. So we assume that there is no effect. We assume that the population, the theoretical, the expected effect is 0. And now we need to test how likely we can get this observed effect or even larger if in reality the expected effect is 0. So how likely we observe this effect by chance. Okay, so we know everything to do that, right? So we know that this is our assumption about the variances, about the standard deviations of the population. In this case, we have a simplified version. We work with equal sample size, but in fact, I simplified it only to make our mathematical expressions on the slides a little bit shorter. It will work also for different sample size, so no worries. So in this case, if we have equal sample size, this is degrees of freedom, and this is what we call a pooled standard deviation, right? So this is the expression we got for the how observed effect varies randomly around the true expected effect. Now let's recall. So this is the observed effect. It depends on the theoretical effect. It depends on the sample size. We know it's random, right? And this is what we call a signal. So this is kind of information we are looking for. This is what we would like to hear. We would like to see, right? So this is a standard error, right? So standard error, it's a variation of this observed effect around theoretical effect. And this is uncertainty caused by a lot of external random factors. So this is our noise. So this is what kind of weaken the signal. And the idea is to estimate how strong our signal is comparing to noise. That's exactly what we also did in one sample t-test, right? So our case is, let's assume that indeed there is no effect. So let's assume that this is our null hypothesis is true. So this is our null hypothesis. How big the observed effect can be? How big this value can be if this is 0? Okay. Well, we can think about this. If this is 0, look, if this is 0, if null hypothesis is true, then this can be removed because it's 0, right? In this case, if null hypothesis is true, this is how the expression should look like. So the observed effect can be as big as this given amount of standard errors, t standard errors, where t depends on the distribution, it depends on degree of freedom, and it depends on the confidence level, right? Now, like in the one sample t-test, we will estimate t as a ratio between the observed effect and the standard error. So it's a signal to noise ratio, right? Signal to noise ratio. For example, in our case, this is the observed effect. Remember, this is the pooled variance, pooled standard deviation. This is the amount of degrees of freedom. So our standard error can be estimated as 2.16. And therefore, the t value will be 5.53. It's a ratio between the observed effect and the standard error. It tells you how many standard errors you can see here, right? So how many? It's 5 standard errors. It's 5.5 standard errors. You already understand it's a lot. Even your sample size is relatively small. We have 6 degrees of freedom. It's a very big number. It's very unlikely to see t-scores equal to 5.5. But how likely? Well, this is the distribution of all possible t-scores if null hypothesis is true and if degrees of freedom is 6, right? So you can see that a lot of things are possible. -2 is possible, +2 is possible, 4 is possible, -4 is possible, and so on. We are here. So this is our t-score that we observe, 5.53. How likely next time we will observe the same or even larger effect? Well, first of all, because in this case, you remember this is when we compare it with 0, so we have no direction. So it means that it's a two-tailed test. So it means that if you have a t-score of minus 5.53, it will be as extreme as you have, 5.53. So this area, you can see how I estimated, right? It's a t-distribution, CDF function for t-distribution. This is a t-score, this is degrees of freedom, and 1 minus because it's a right tail in this case. It's 0.00074. This area, in this case, it's the same, 0.0074. And if I take a sum of these two areas, I will get my p-value. So this is the chance to observe t-score 5.5 or bigger if we repeat our experiment again, and if the expected effect is 0. It's a very small chance. So it means that if you repeat it 1,000 times, only in 1 out of 1,000, a little bit more, right? Almost 2 out of 1,000, you can observe this value. It's very unlikely. So you should be very unlucky to observe it just by chance. So therefore, it will be reasonable in this case to reject null hypothesis and claim that indeed you have an effect. Okay. So this is the result. So we have observed effect of 11.9. It's a positive effect. So increasing time indeed increases the percent of popped corns. Of course, this kind of funny example, right? Who cares about percent of popped corns? But the point is that you can do it for any experiment like this. You can change catalyst and see how much more yield you get. You can do the same things for any experiment where you change one factor from one level to another and measure the outcome. So that's the way to estimate the effect, the observed effect, and the theoretical effect, right? So in this case, this is the observed effect. This is the expected effect, how big the expected effect can be. And this is the chance that you observe as big effect as you have, or larger, if in fact the theoretical effect is 0. So it means that you don't have effect. It's just by chance you observe this. Okay. So this is the way to estimate your effects. And then you can show this effect as two plots, either like this one, where you have the average here, and this is the individual standard errors, or even better, if you show it like this, where you already show a difference, right? So this is a difference of the means you observe, and this is the lower and upper boundary of this confidence interval. Okay. So again, I will show you how to do it in R. It's the same procedure I showed you before. You define the vectors, you provide these vectors to t-test. Remember that you need to tell that variance equal to true. It means that we assume that the variance of populations are the same because we didn't change any external factors. And this is the outcome you get. So you can see that this is the p-value and this is the confidence interval. Now it's full outcome, not just confidence interval. And you can see although it's a little bit different from what we got, it's very, very close to the values that we got. And the difference is just because I round a lot of things when I did my calculations in order to make calculations a bit easier. Okay. Now let's talk about this little issue, right? So you remember that we always assume that sigma 2 is equal to sigma 1. It makes additional requirements for your sample. If you cannot be sure in this, if you have any doubts, then you need to run a t-test without this assumption. So in this case, the R, in this case I use R, you can see, will run a special modification of the two-sample t-test. It's called Welsh two-sample t-test. And the idea is following. It will, first of all, it will have a bit different degrees of freedom. It's a little bit weird. You can see instead of 6, you have 5.009. And then you can see that the p-value will be a little bit larger. The standard deviation will be, or the confidence interval will be a little bit wider. But you can see, for example, the t-score in this case, it's the same, right? So this one, it just simply takes into account the possible uncertainties that came from unequal standard deviations, unequal variances, and therefore sometimes it gives you a little bit more precise results. So strictly speaking, if you cannot be sure about this, just run t-test in the default option, and then these results will be quite trustworthy. Okay. Now you remember that we can use t-distribution and we can use t-test if either values came from normally distributed population, or if your values, if your sample size is big enough, you remember about 30, right? In this case, you cannot treat all your sample, the whole sample, as one sample came in from one population. For example, if you make a cuckoo plot, you can see that all values from this sample, they are here, and all values from this sample, they are here. So you can clearly see an effect of two populations, right? You can clearly see an effect of two populations. But how to assess normality here? Well, one case is to assess normality individually. Take one sample and second sample. But the problem is you have 4 values here and 4 values here. And you remember that if you have less than 6 values, it's difficult to assess normality. You simply don't have enough power to assess normality if your sample size is below 6. However, you have a little trick here. What you can do, you can recall that these values came from this population, right? These values, they came from this population. Here you have normally distributed values. Here you also have normally distributed values. And then we assume again that the sigma are the same. Now, what if you take a difference between x and mu, right? It's like standardization without dividing to standard deviation. Then you will get the difference will be distributed like this, normally distributed with standard deviation equal to sigma and average equal to 0. And this difference will also be normally distributed with average equal to sigma and standard deviation equal to sigma and average 0. So it means that if you consider not values, but difference between values and their mean, you can treat them as coming from the same population. And that's the trick we can make. So we can take the values and we can subtract the mean from the values. You can see this is the mean value. This is the mean value. We can say if we don't have any random part, then all these values should be the same, because they came from the same population. All these values should be the same because they came from the same population. But because we have random part, we also have residuals. Residuals, it's a difference between the real value and the mean. So it's simply this one. It's simply x minus m. So in this case, x1 minus m1. This one is x2 1 minus m1 and so on. So you can see like this one is 30.1. So this is x21. This is 32.6. If you take 30.1 minus 32.6, you will get minus 2.5. So these are x minus m values. And these values can be treated as coming from the same population with average equal to 0. Now you can make a plot for residuals. And you can see that they are very nicely distributed. You don't see this systematic effect anymore. So indeed, this looks like random values coming from normally distributed population. And in this case, you have enough values to assess normality. Okay. So that's the procedure we are going to use also in all next methods. So first of all, remove all systematic effects. For example, if you assess average, remove average values, subtract average values. And what you have left is we call this residuals, and we check normality of residuals because that's exactly what we assume to be normally distributed. Okay. So I have raster up, which shows you how this two-sample t-test works. And the next video will be about this raster up. Then I recommend you to go to Raster and try this up, play a little bit, change different parameters, look at different plots and so on and so forth. And then come back for the next video where we will talk about what to do if you have more than just 2 levels.